Now we will see that a magnetic field can also be interpreted as a relativistic correction to the electric field. And in order to show that, we're going to assume that we have two isolated charges Q at a distance r moving with velocity v in the x direction. So two isolated charges Q at a distance r moving with velocity v is equal to vi hat, so in the positive x direction. Now I can look at this from two different reference frames. The S frame, the lab frame, is the one in which the charges are moving with the uniform velocity vi hat, and the proper reference frame in terms of theory of special relativity, that is the reference frame in which the charges are stationary. So this reference frame, S prime reference frame, is moving with respect to S reference frame at rest with a velocity v. So S is at rest, S prime has a velocity v with respect to the S reference frame. Now if you remember our Lorenz transformation equations for this from our previous studies on modern physics, well, the Lorenz transformation tells us that there is a velocity transformation between these two reference frames, such that in the lab reference frame, velocity component, x component measured in the lab reference frame is a velocity component ux prime measured in the proper reference frame plus v, the relative speed of the relative velocity of the two reference frames, divided by 1 plus ux prime v over c squared, where c is the speed of light. And if you have an object moving on the y-axis that is being observed by two observers at these two reference frames, the velocity reported on the S reference frame, uy, is uy prime divided by gamma 1 plus ux prime v over c squared, and that comes from the fact that we have time and distance, so time dilation and length contraction transformation between these two reference frames. So what I would like to figure out is the force that appears between these two charges in the two reference frames. So in the S prime reference frame, the proper reference frame, there will be no force on the x prime axis, no x prime component. On the y prime axis, we have Coulomb's law, 1 over 4 pi epsilon 0, q square divided by r prime square. And for the z-axis, we also don't have any force. Now, how can I perform a transformation of the force to the S reference frame? So, basically in this scenario where I'm observing the moving charges, since I have dx prime is 0 and ux prime is 0, this transformation is telling me that uy is equal to uy prime divided by gamma, and the time I can observe the time dilation dt is equal to gamma times dt prime, where dt prime is the proper time measured in the proper reference frame. So with that, if you look at the force in the lab reference frame and you look at the force in the proper reference frame, so once again I have uy is equal to uy prime over gamma, and then I have dt is equal to gamma dt prime. So from this equation I can write duy is equal to duy prime over gamma, and then here I have dt is equal to gamma dt prime. So if you look at duy dt, that is 1 over gamma duy prime over gamma dt prime. So I would get 1 over gamma squared duy prime over dt prime. So basically that is acceleration on the y-axis as reported by the S reference frame is square root 1, not square root because it's gamma squared, 1 minus v square over c square, acceleration reported by the S prime reference frame. So if you just add a mass here, that would convert this to a force, then you would see that the way the force translates from S prime to S reference frame is Fy is 1 minus v square over c square Fy prime. So basically the force in the reported in the S reference frame for Fy would be equal to 1 minus v square over c square q square over 4 pi epsilon 0 and r square. So r is equal to r prime here because the motion is on the x-axis, no length contraction on the y-axis. Okay, so we have found out that the force in the lab reference frame is 1 minus v square over c square q square over 4 pi epsilon 0 r square, and also recall that the speed of light is given as 1 over square root epsilon 0 mu 0 from electromagnetism course. Okay, so this is going to give me for the force q square over 4 pi epsilon 0 r squared minus if I substitute for c square 1 over epsilon 0 mu 0, this is going to give me minus mu 0 over 4 pi q square v square over r square. So I substituted for c square 1 over epsilon 0 mu 0. All right, so I can rearrange this force. I can write this as q times q over 4 pi epsilon 0 r squared plus q times v times minus mu 0 over 4 pi qv divided by r squared. And if I write this force as a vector, this is going to be equal to q over 4 pi epsilon 0 r squared in j hat direction. So if I consider the charge on the top, and then I have plus qv minus mu 0 over 4 pi qv over r squared, again in j hat direction. Now if you look at the cross product between the unit vectors I hat, j hat, k hat, we see that from cyclic permutations I hat cross j hat is equal to k hat, and similarly if you look at I hat cross k hat. So that would be, this is the positive direction. So if you go from I hat to k hat, you would be going in the negative direction. You will reach j hat. So instead of j hat, I can write so for minus, or we will reach at minus j hat. So instead of this, I can write minus I hat cross k hat, so put the minus sign on the left, is equal to j hat. So I realize that this force is q times, well, this q divided by 4 pi epsilon 0 r square is electric field created by this charge. And then I have minus mu 0 over 4 pi qv squared over r squared minus I hat cross k hat, which is the which is the j hat direction, and then I can basically recall that my velocity was in I hat direction. So velocity is in I hat direction. So instead of writing it this way and operating the minus sign on the left, I can see that this force can also be written as q times the electric field plus the velocity cross product with mu 0 over 4 pi qv over r square k hat. So I have taken care of this minus sign. This minus sign became plus, and then I have noted that velocity can be written as v I hat. So the charge times the velocity v, it is, I can call this as I times delta L. So I is dq dt, charge flow per time. So v is dx dt. So I can write this as I delta L, where delta L is current element swept out by a charge q in a unit time when moving with velocity v. And we can basically write this as delta L, because the charge is moving in the positive I hat direction, as a vector delta L I hat. And for the r hat vector, I can define j hat, and I have I hat cross j hat is k hat. R is the radial vector between the distance vector between the two charges. So with this, I can write the force as a vector once again, q electric field plus v cross mu 0 over 4 pi I, the cross product of the current element with r hat divided by r square. So that basically takes care of the k hat. So we can see that this force F is actually q times electric field plus velocity cross product with magnetic field B. So that is known as the Lorenz force. And here the magnetic field B is given as mu 0 I over 4 pi delta L cross with r hat over r square, which is also mu 0 times the magnetic field H. So H is I over 4 pi delta L cross with r hat over r square. So either for B field or H field we can write the same, it's the same thing, and what we have obtained here is known as Biot-Savart law. So we can see that if you just follow the relativistic transformation from the reference frame of the moving charges, the proper reference frame, to the lab reference frame, we see the appearance of this magnetic field H or B, which is mu 0 times H. So the end result is that magnetic field that we measure in the lab reference frame is merely a relativistic correction to the electric field and magnetic field is produced by moving charges. So that's an important conclusion. It's a little bit advanced calculation that we have done here, but basically if you can review your Lorenz transformation in the theory of special relativity, this result is quite simple. So once again, I have two isolated charges, q at a distance r, moving with velocity, uniform velocity v in I hat direction. In the lab reference frame, which is at rest, I can see that these charges are moving with velocity v in the positive x direction. In the proper reference frame, that is the reference frame of the charges, they're not moving. The reference frame, S prime reference frame, is moving with velocity v with respect to the lab reference frame at rest. The Lorenz transformation for this scenario has the following equations, where I see that the velocity transformation is ux equals ux prime plus v over 1 plus ux prime v over c square, where c is the speed of light, and which is equal to 1 over square root 2 mu 0 epsilon 0, and uy is uy prime over gamma 1 plus ux prime v over c square. And this gamma, so let me note here, is the relativistic correction factor. Gamma is 1 over square root 1 minus v square over c square. Okay, so looking at the force that appears in the proper reference frame, the charges are at rest in this reference frame, and there is just the Coulomb force 1 over 4 pi epsilon 0 q square over r prime, where r prime is the distance between the two charges, square. R prime and r are actually the same in the two reference frames because the motion is on the x-axis, not on the y-axis. So there is no length contraction. So because these charges are not moving on the x prime reference frame, on the x prime direction, dx prime is 0 and ux prime is 0. So the transformation is quite simple. The velocity on the y-axis, uy, is uy prime over gamma, and Time dilation tells me the proper time dt prime measured in the proper reference frame multiplied by gamma. It's dilated in the lab reference frame, gamma times dt prime. So because the force is related to, is given by mass times acceleration, if you just look at how the acceleration transforms between these two reference frames, uy equals uy prime over gamma, duy equals duy prime over gamma, dt is gamma dt prime. You can see that the acceleration transforms as 1 over gamma squared times acceleration in the y in the prime reference frame. So the force on the y force in the lab reference frame is 1 over gamma squared times the force in the S prime reference frame, which is 1 minus v squared over c squared times fy prime. Now I substitute for the speed of light 1 over square root epsilon 0 mu 0, and I expand this and I see that I have the force having q times q over 4 pi epsilon 0 r squared plus qv times minus mu 0 over 4 pi qv over r squared. Well, so if I write this as a vector, so if I consider this as the force acting on the top charge, it's in plus j hat direction. So all of these terms will have a plus j hat added to them to write it as a vector. And then I realized that the q over 4 pi epsilon 0 r squared in j hat direction is the electric field. That is due to the bottom charge. And then I have for the minus j hat direction, I can write I hat cross k hat, or for minus I hat cross k hat is j hat. So I have a minus mu 0 over 4 pi qv square over r square j hat, where j hat is minus I hat cross k hat, minus signs cancel. So this is basically I hat cross k hat. So velocity is a vector, it's v I hat. So instead of writing this as v square I hat, for v I hat I can write v vector. So it's v vector cross product with mu 0 over 4 pi qv over r square k hat. So I'm substituting v I hat into this. So for v square I hat, I have v I hat is the v vector. And for qv, I can see that this is basically the current I multiplied by the length of the current element, which is swept out by a charge q in a time unit time when moving with velocity v. So this because the charge is moving in the I hat direction, it's delta L I hat when written as a vector, and the distance between the two charges, well, the radial vector is unit vector is j hat. So I hat cross j hat is k hat. So for k hat I can write, so basically I'm substituting for qv I delta L. So I delta L appears here for qv, and written as a vector it is delta L vector cross with r hat divided by r square. So I can see that this is QE plus V cross with B, and that's basically where B is recognized as mu 0 I over 4 pi. I is our current. The current element delta L vector cross with r hat over r square, which is also mu 0 times h, where h is I over 4 pi. Delta L cross with r hat over r squared. That's Biot-Savart law, and the force that appears in the charge is Lorenz force. It's QE plus V cross with B. So we find that a magnetic field measured in the lab reference frame is a relativistic correction to the electric field. It is produced by moving charges. So if you have charges moving with velocity v with respect to the lab reference frame, you will be measuring a magnetic field.